Well, hello, this is Matt Roscoe from the University of Montana, and here is a video lecture for our Section 5.3 on Wilson's theorem in the course Math 326 Number Theory. Okay, well, let's take a look at what's on deck here. I want to start out by telling you a little bit about the history surrounding this particular theorem. It's surprisingly recent. And then I'll go ahead and just present Wilson's theorem, and we'll work through the proof. We'll talk about the converse, and then I'll give a quick example. And then we'll spend some time talking about how both Wilson's and Fermat's theorem, little theorem, come together to give us a little intuition about quadratic congruences. Remember, we've already sort of thought about linear congruences. We sort of have that problem solved. So the next obvious place to go is quadratics, and it turns out that we do get a little bit of a toehold here from Wilson's, and then we'll end on an example using that result. Okay, so historically, it was 1770 when the English mathematician Edward Waring included in his Meditations on Algebra an interesting property of primes that his student John Wilson had discovered. And so it's aptly named Wilson's theorem, but no proof was provided, and it caught the attention of Lagrange, who just a year later provided a proof of Wilson's theorem. So let's go ahead and dive right into it. Here it is. Here's Wilson's theorem. It says that if p is prime, then p minus 1 factorial is congruent to negative 1 mod p. P minus 1 is prime, then p minus 1 factorial is congruent to negative 1 mod p. Okay, let's take a look. All right, so maybe we should work through a couple examples just to make sure we understand what's going on. So we have to have p as prime. So let's take something like p equal to 7. And we're told by Wilson's theorem that if p is prime, then p minus 1 factorial is congruent to negative 1 mod p. So if we apply that to this situation, then what we would have is we would have 7 minus 1 factorial congruent to negative 1 mod 7. So that would mean that 6 factorial is congruent to negative 1 mod 7. Let's just check to see if it really is. Let's see, 6 factorial would be the same thing as 6 times 5 times 4 times 3 times 2 times 1. So really we're checking. I mean, obviously this is going to work out because it's a theorem, but let's just make sure it really does work. One important thing to think about right away is that this number 6 here is congruent to negative 1, right? So maybe we'll just strip that off and call that negative 1 times 5 times 4 times 3 times 2 times 1 congruent to negative 1. So really what the theorem is saying is that everything less than p minus 1, I guess this part right here, that's all got to be equal to 1, right? So let's just sort of think about why that would be the case, and recall that we're in mod 7 here, right? And I think it's pretty easy to see why this happens. If you pair these up, I mean, first of all, we don't really need to think about 1 at all because 1 times anything is going to be 1. So that leaves even number left here, 2, 3, 4, and 5. And if we're just careful about the way we pair them up, we can see quickly that the pairs are congruent to 1. And I think the right way to pair them is to take a look at, let's see, it'd be 5 times 3. 5 times 3 is congruent to 15, which is congruent to 1 mod 7. And then, so if 5 and 3 pair to make 1, then that means 4 and 2 must pair to make 1 as well. 4 times 2 is 8, which is of course congruent to 1 mod 7. And so we can definitely see that the way this works is that important numbers seem to sort of pair up, these two circled numbers and these two boxed numbers, to make a 1 in the factorial argument, leaving just the 1 on the end and the 6 on the front. And the 6 on the front, of course, is equal to p minus 1. Let's try just one more example. we'll bump it up to 11. So what Wilson's would say here is that 11 minus 1 factorial should be congruent to negative 1 mod 11. That means that 10 factorial is congruent to negative 1 mod 11. And let's just play the game again. Let's take a look at 10 factorial. So it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And supposedly we're checking to make sure this is congruent to negative 1 mod 11. So right away what we notice is that the 10, that's the negative 1, right? This modding by 11, we can say that 10 is congruent to negative 1. So that means all of these ones in here must pair up somehow to make ones, or maybe triple up. But I think the right idea here is to pair them. I'll try to do this as best I can here. What we're looking is for a product that's one more than a multiple of 11. So one that just jumps off the page right away is 12, and one of those products is right here. 6 and 2 would pair up because they make a 12. So that's 12 congruent to 1 mod 11. Let's see, another way that we could make a 12 would be 3 times 4, right? They would pair up to make 12, which is congruent again to 1. Let's see, what would go next? Let's see, let's try to figure out what 5 pairs with. Could 5 pair with 7? If 5 pairs with 7, we get 35, which is not one away from a multiple of 11. If 5 pairs with 8, we get 40, which is not one away from a multiple of 11. I guess, 44 would be the closest, or 33. What about 5 with 9? 5 times 9, that's 45, which is one away from a multiple of 11. So those two pair up. I'll just sort of try to draw this down here a little bit. So 5 times 9 is 45, which is one away from a multiple of 11, one greater, so it's congruent to 1. And so that really just leaves us with one more to pair, and this better work out, right? If the theorem's going to be true. But 8 and 7, when they pair up, we get 56, and 56 is indeed one away from a multiple of 11, 55. So again, you can kind of see the way this works. All of these numbers seem to pair up in strategic ways so that we get these nice cancellations. In effect, they're all just ones. So maybe I'll use some tools here just to make this completely clear. So I guess 8 and 7 pair up to make a 1. 9 and 5 pair up to make a 1. What's 6 and 2 pair up to make a 1, and then just one more. 4 and 3 pair up to make a 1. And this seems to be the general case, right? That up here when we had 7 as our prime setting, modular setting, we had this simple pairing of 5 and 3 and 4 and 2. So here it would be, 5 and 3 paired up to make a 1, and 4 and 2 paired up to make a 1. And what we're left with then is just the 6 and the 1, and the 6 we think of as negative 1. Here all of these numbers all paired up, and what we're just left with is the 10, which we call negative 1, and the 1 on this end, which of course isn't going to change anything. So our 10 factorial is certainly congruent to negative 1. It's kind of an interesting setting, and we'll see that the proof actually is really similar to, I guess, the numeric example we're given here. So let's go ahead and dive into the proof. All right. So make sure I'm on. So here's our hypothesis. If P is prime, then p minus 1 factorial congruent to negative 1 mod p. Okay, so let's go ahead and try to prove this. Okay, so the proof, you know, what we do is we sort of get rid of the first couple cases, so just looking at them. So if p is equal to 2, then what? 2 minus 1 factorial, that's equal to 1 factorial. And in the setting where we're talking about 2, 1 factorial, well, that's just 1, and 1 is actually congruent to negative 1 mod 2. You have to think about that a minute, right? I could subtract 2 from 1 and I would get to negative 1. So this is the only case, I think, where 1 and negative 1 are congruent in a modular setting. If p is equal to 3, then what do we get? We get 3 minus 1 factorial. That's 2 factorial. 2 factorial is 2 times 1, so that's just 2. And 2 subtracting 3 is negative 1 mod 3. So it certainly works for 2 and for 3. So now take p to be strictly greater than 3. Then let's let a be any one of the integers from 1 to p minus 1. So I'll just put 1, 2, 3, 4, dot, 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 all the way up to p minus 1. Okay. So a is chosen from this set. And consider the linear congruence. Here we go. AX congruent to 1 mod p. I'm going to call this equation star because it's pretty important. Now, one thing to notice is that a is selected from here, right? And since any number that's less than p will be relative prime to it, then we know that the GCD of a and p is equal to 1. And if that's the case, and 1 divides 1, then we know from our theory of linear congruence that there's exactly one solution. So I'll just say since the GCD of a and p is equal to 1, there is exactly one solution modulo p. Let that solution in each case be called A prime. Okay, so that means for every choice of A up here, the solution to this is going to be A prime. So what we would get is we get something that looked like this. A times A prime has to be congruent to 1 mod p. Okay, so really what you should be thinking is, oh yeah, this is just 6 and 2 or 4 and 3 or 7 and 8, because we know that 8 times 7, right, is congruent to 1 mod 11. Okay, now the important part here is that we want them to pair up, right? We want them to pair up, so we want the ones in the middle, you know, for A and A prime not to be the same thing, right? They need to pair up in pairs of 2. So so it's important to start out with the ones that do pair up, and it turns out, or that don't pair up, and it turns out that the first and the last ones are the ones that are the only ones that where A and A prime are the same. So let's just take a look. And I will just write it this way. Now, it can be concluded that that A congruent to A prime equal to A prime mod P if and only if A is equal or congruent to 1 mod P, or A is congruent to P minus 1 mod P. So those are the two cases where the product, I guess, the solution here, when I start with that A, this A in that position, then the solution here is also equal to A. Okay, so let's just show that that's true. So for the forward direction, so really I'm kind of proving a little mini theorem in here, right? So for the forward selection, we have to say that, you know, if A is equal to actually it's for the, I'm just trying to think here, it's actually for the backward direction. So let's do that now that I think of it. So we got two things to show. For each one of these choices, we want to show that it results in A and A prime being equal. So let's go ahead and see what happens if I choose A equal to 1. So the first thing I guess we have to show is that if A equal 1, shoot, my eraser's given out. So number 1, if A is equal or congruent to 1 mod P, then what do we get? Then what we're trying to solve is 1x congruent to 1 mod P. Well, that's pretty easy to see that that implies that x is congruent to 1 mod P. And when x is congruent to 1, that's, you know, that's the solution up here. That implies that A prime is 1. Okay, so that's the first one. 2, let's see, a little bit harder. If A is congruent to P minus 1 mod P, then what am I trying to sort out there? Then what I put in A right here into my linear congruence. So it's P minus 1 times x. We want to solve that equal to 1 mod P. Well, I guess we could distribute the x. We get xp negative x congruent to 1 mod P. I think it's easy to see that xp is a multiple of p, so this one's just congruent to 0. We get negative x congruent to 1 mod P. And then multiplying both sides by a negative 1, we could get x congruent to negative 1 mod P, which means that x is congruent to P minus 1 mod P. And what we've shown then is that this solution, the solution here, is P minus 1. So P minus 1 times P minus 1 is actually congruent to 1. And that implies then that so A prime is congruent to P minus 1 mod P. Okay, so we've done the backward direction. We've shown that, you know, if you're in either of these two settings, then this particular equation solves for itself. In other words, one, if a is 1, then x is 1. It's kind of easy to see that. It's not so easy to see that if a is p minus 1, then x is also p minus 1. But here's the argument for that. But we do need to do the forward position, or the forward direction. Remember that we called this an if and only if here, so we have to go for the forward direction next. Let's try that next. For the forward direction, let's let A be congruent to A prime mod P. Okay, so what we want to show is that if we adopt this, then the only A that could result, right? The only A that could result are these two, right? 1 and P minus 1. Okay, so let's try to get this. Then I guess what we could do is we could multiply if A is congruent to A prime. Oh, okay, yeah, if A is congruent to A prime, then for, let me just stop here for a sec. Yeah, now I got it. So then, so if A is equal to A prime, then examine whether or not the product of these two could be equal to 1, right? Okay, so here we go. A times A prime equal 1 mod P. Okay, well, since I have A times A congruent to A prime, I can replace either one of these with either A prime or A. So this is the same thing then as A squared congruent to 1 mod P. And then I'm going to go ahead and subtract 1 from both sides, so it'll be A squared minus 1 congruent to 0 mod P. This side then we can factor A plus 1 times A minus 1 congruent to 0 mod P. Now, anytime we have a product equal to 0, it implies then that, you know, each one of these has to be 0. That's the only way we can get a 0 both in integers as well as modular arithmetic, since we're multiplying. So we get kind of two branches from this. It says that either A minus 1 is congruent to 0 mod P, or A plus 1 is congruent to 0 mod P. I didn't like the way I wrote that there, so I'm going to switch the signs up here. Minus, plus. Okay, well, so this one implies then that A is congruent if I add 1 to both sides. And this one, if I subtract 1 from both sides, I get A congruent to negative 1 mod P. And then I recognize this as negative 1 adding P to it would give me P minus 1 mod P. So I guess what we've found is that anytime the A primes are equal to 1, and anytime A is equal to A prime, when I'm trying to solve this equation and choosing my A's from here, anytime you know, the number that we solve for is equal to the number that's, I guess, in the, you know, the coefficient that leads the linear equation. If they're equal, then it leads to just these two. So another way of thinking about this, I don't know if you're sort of thinking about this, what we're really finding is we're finding multiplicative inverses here, right? We're saying, given an A, what is the number that I multiply by to get 1, right? So, multiplicative inverses, we're used to, 2's multiplicative inverse is 1/2, and 3/2's multiplicative inverse is 2/3. But what we're finding are multiplicative inverses in a modular sense, right? And what we've just found is that in the setting mod p, 1 is its own multiplicative inverse, and so is p minus 1. So those two numbers just pair with themselves. And the rest of them then must have a unique or different multiplicative inverse. So we've sort of got that sub-goal done, and we say now omitting 1 and p minus 1, we now must be able to group the remaining choices and the remaining choices are 2 now, 3, 4, all the way up, not to p minus 1, but p minus 2, right? And we can group these remaining choices into pairs. I'll call them A and A prime not equal to A, right? Such that A times A prime is going to be equal to 1 mod P. So now when we pair these, it's going to turn out to be p minus 3 divided by 2. So that's how many pairs. And multiply, we get that 2 times 3 times 4 times ... all the way up to p minus 2. That has to be congruent to 1 mod p, right? So in a sense, what I'm doing here is I'm trying to sort of point at these ones in the middle, right? They all pair up, and when we pair them all up, they pair up each with a pair to make a 1. So when we pair all the ones up, we get just a 1, which gives us, I guess what I can do is multiplying, I guess, what is this? This is the same thing as p minus 2 factorial is congruent to 1 mod p. And now we can get to Wilson's pretty quick. We just multiply by the one thing that's missing, which is p minus 1. So p minus 1 factorial would be congruent to p minus 1 mod p. And p minus 1 we recognize as -1, or just p minus 1 factorial congruent to -1 mod p. And that's what we wanted to show. That's the statement of Wilson's. So it takes a while to get there, and the numeric example is pretty helpful. I think it really gives us a sense of how to construct the proof. But let's take a look at how it might help us understand, I guess, a specific question. I did want to mention this, that there is a converse to Wilson's theorem, and I'm not going to prove it here, but the proof is in your book, and it says that if this is true, if n minus 1 factorial is congruent to -1 mod n, then n must be prime. And this is kind of an interesting anecdote. What we have here is a method for testing primality, but you have to question the utility of this, right? I mean, I think it's pretty obvious to see, it is a necessary and sufficient method for determining primality, but it's really computationally cumbersome. So, for example, I mean, just take a big number like 1,373. So, if you wanted to check that as prime, what you'd have to compute would be 1,372 factorial, right? And then reduce it mod 1373. So, it's sort of just probably as cumbersome as a brute force search or trial division itself. So just a little side note, the converse is actually true too, but it's of little utility, at least in terms of determining primality. Okay, let's take a look at an example, and then we'll move on. So let's take a look at 18 factorial. We're told to show that that's congruent to -1 mod 437. Okay, so let me move over to my Elmo cam. There we go. Well, the first thing we should ask is 437 prime? And it turns out that it actually is no. The check would be, of course, to take the square root of 437. It's roughly in the neighborhood of 20. And then what I usually do is start at that limit and go backwards. So if I just tried 19, the first thing that happens is 437 divided by 19 turns out to be 23. So that means that 437 is equal to 19 times 23. And so right away we're sort of like, oh, well, we can't use I guess, Wilson's theorem on the modular setting 437, but we could use Wilson's theorem on the modular setting for 19 and 23, and then hopefully maybe combine them to get something in mod 437. So let's try that. Let's take a look at what Wilson says in each of those cases. So Wilson's mod 19 would say that 19 minus 1, or 18 factorial, is congruent to -1 mod 19. Oh, that's nice. Okay, so this works mod 19, and 19 divides 437. So perhaps we could use that to help us. I guess what this really means is that 19 divides 18 factorial plus 1, right? Let's take a look at how it works for 23. So for the 23 setting, what we would have is that 22 factorial is congruent to -1 mod 23. And what we really need to get to is 18 factorial, not 22 factorial. So I would suggest that we just create it, right? What we could write here is we could say, well, this is the same thing as 22 times 21 times 20 times 19 times 18 factorial. That's the left-hand side, congruent to -1 mod 23. Sorry, I'm going off the page there. I should have given myself a little more space. So let's think about this. Then we could just reduce these modularly. You'll have to do a little work to do this, but if you multiply 22 times 21 and then reduce it mod 23, what you'll get for an answer is 2. And if you, I guess, multiply 20 and 19 together and then reduce mod 23, what you'll get is 12. And that works out nice because 12 times 2 is 24. And so that's just a 1. And so that means that I can basically ignore these first 4 digits, or first 4 integers in this left-hand side, and just say, well, this is the same thing as 18 factorial congruent to -1 mod 23. And what that means then, I guess, is that 23 divides 18 factorial plus 1. So I guess, we'll call this 19 and 23 both divide, and since since the GCD of 19 and 23 is equal to 1, we can state that 19 times 23, right, divides 18 factorial plus 1. And what that really means is then that 437 divides 18 factorial plus 1. And so 18 factorial must be congruent to negative 1 mod 437. Well, I hope that makes sense. So we took advantage, I guess, of Wilson's here and here. We had to do a little work on this one to get to a similar statement for 23 as for 19, and then the fact that these are relatively a prime allows us just to multiply the result. So if 23 divides this and 19 divides this and they share no common factors, then obviously this number must be a multiple of both 23 and 19. Okay, hope that makes sense. I think I'll go ahead and stop right now. I'm a little out of time, and I'll post a second video on the congruence half of the chapter. So for now, bye for now, and I'll post another video here for the second half of the chapter.